So this is a re-recording of a talk I recently gave for a seminar course at my university, talking about the history of solvability. I figured since I made the slides, I'd make a version here for YouTube. So just a couple side notes about this. I mean, originally this was supposed to be a 20-minute presentation. So there's many details, many interesting details that are missing from this discussion. And I suppose the other thing to mention, I forgot. So we're just gonna go ahead and dig into this. So um, a polynomial, remember, is said to be solvable, or we say solvable by radicals, if its roots can be expressed in terms of the coefficients using any combination of addition, subtraction, multiplication, division, or nth roots. So, for example, if we just have a linear equation, what can I plug into x to make it equal to 0? Well, there's just one number, and it's going to be minus a naught over a1. Okay, pretty simple, right? Now, in high school, you probably learned that a polynomial, a second-degree polynomial, we can explicitly determine its roots by the quadratic formula. So again, I mean, what are we using? Addition, subtraction, multiplication, and the square root symbol in some combination. Now, the original history, the first, recorded instances of anyone working on these things was actually the ancient Babylonian mathematicians. But their conception of solving quadratic polynomials was so vastly different than what we have today. I mean, first off, this was thousands of years before anyone accepted complex numbers. And for example, I mean, they didn't write down symbols and equations, right? They were thinking geometrically. If you know these works where they work these things out, I mean, it's basically all in words and pictures. So of course, we're not going to get the full quadratic formula until much later, but more or less the polynomials that could be solved. We figured out. I should mention this this picture at the bottom here is an example of completing the square. So they basically, the ancient Babylonians figured out how to complete the square, but it would look very different than the way we normally think about it today, and they would not have been able to determine complex roots, of course. So then along comes our man Omar Khayyam, and he's the first person to sort of make significant progress on third-degree polynomials. He made a systematic classification of the types that there were, and he had a method based on using intersection points of conics that he actually got from the Greeks, but very far from a full solution. Things start kicking up a bit when the famous Fibonacci, whose real name was, or I mean, I guess they're both real. His name was Leonardo of Pisa, and for a while Europe was stagnating in terms of mathematical development, and it was at this time that more in the Middle East, and people like Omar Khayyam and Al-Khwarizmi were making great advances in all sorts of aspects of algebra. And so Fibonacci is actually responsible for bringing a bunch of that knowledge back over to Europe and sort of re-kicking off at least an interest in algebra. And he actually believed that the cubic was not solvable in radicals. So perhaps I didn't mention this before, but so we've seen explicitly, we do know now, right? Linear equations and quadratics solvable in radicals. Cubics, Fibonacci thought not, because he had a pretty tough time trying to show it. So then flash forward a little bit later, Italy, around the 14 to 1600s, basically had the equivalent of rap battles, but with math. People would like challenge each other with hard problems, try and make it so the other person couldn't solve it, but you would have to have the solution, and then there'd be like public displays. So I went digging in the archives, and I found this picture from the year 1500 of Tartaglia, who looks an awful lot like Eminem in this picture, and just throwing down in a math battle. Um, I mentioned this for the context because Del Ferro was actually the first person to solve the cubic by radicals, like completely. However, he wanted to keep an upper hand in these supposed math battles of the day, so he kept it a secret. But he did mention it to his students Fior and Nave on his deathbed. But perhaps they didn't have the greatest ability to use his solution. We'll see why in a second. So I shouldn't have called Tartaglia earlier. I want to stick to calling him Niccolo Fontana because Tartaglia is a nickname he got because he stuttered. He had a mouth injury as a child, and then he stuttered, and Tartaglia literally translates into stutterer. So I figure I'll have some respect. I'll call him Niccolo. And he claimed, he announced publicly that he had a solution to the cubic. So naturally, Fior, having Del Ferro's actual solution, was like, "Oh, I'm gonna take this guy down." But for whatever reason, when he challenged him, Fior lost still somehow, and Nicolo, whether or not he had the full method, he was able to make easy work of all of Fior's problems. So hearing about this, the mathematician Cardano, he wanted to offer Nicolo money for his solutions. And it's kind of funny. So I think maybe this was the plan from the get-go. If anyone knows about, there's this cryptocurrency called Cardano, and the dude who invented it recently donated millions of dollars to start a research institute specifically based on foundations of mathematics, and namely with things like automated proof assistance in mind. So I think he was planning on making such a donation from the get-go. I don't know. Maybe it was just a cool math name. Anyways, Nicolo rejects these first couple offers. But eventually, like the bread and butter of mathematicians, yeah, we had battles about cubics back then, but like today, engineering is where you make money. So Cardano was like, yeah, you can show your military inventions to the Milanese court, and Nicolo was like, yeah, I'll take that. So, but he posed a stipulation to Cardano not to publish his work on the cubic. Cardano really didn't want to, but okay. And I mean, some people have even suspected that Cardano wasn't even given the full solution by Nicolo. And as I mentioned before, there's some doubt, like, did Nicolo really have the full proof? There's, some authors have argued that he's tried to take responsibility for other people's work in the past. But Cardano, he kept his mouth shut, but he really was like stoked on the fact that we had finally like outdone ancient mathematicians in this significant way. We had solved the cubic, something they couldn't do. But eventually, word got out that Del Ferro was actually the first person. So Cardano was like, well, if you weren't really the first person, maybe I can just, publish anyways. So he did. Nicolo was not too happy about it. Now, I should mention, all these pictures are from Wikipedia, except for this one. You can see is from biography.info. So Cardano goes on with his student to still, develop the full solution of the cubic, publish on it. Okay, they weren't really the first to it. And then they go and they're like, well, the next question is, okay, cubic solvable by radicals. Is the quartic solvable by radicals? So their method, and we'll see this is important later on, the Cardano-Ferrari method was about making a linear change of variables to first get rid of the x squared term, which they found was always possible. And then the solution is given by this. So after making that change, this is the cubic formula basically. So we can see it's solvable, right? There's just different kinds of roots involved, multiplication, addition, whatever. Interesting side note, this is where we got the first hint that complex numbers are legitimate, because basically what would happen in here, you see there's this minus sign inside these roots. When working through this and trying to simplify things, there are places where it would look like for a second you had to take a square root of a negative number. These things would cancel out eventually, but there was always this, like, it was lurking around there. So you'd start with real numbers, you'd end with real numbers, and somehow you pass through complex numbers on the way. And this, I think, was instrumental in people first thinking that there's some legitimacy to the complex numbers. So the full solution of the quartic actually did appear in Cardano's work in many separate cases, but technically it's Ferrari who really gets full credit here. So they really took that information and ran with it. And here's the quartic equation. So you can see how zoomed out this is on the slide, and it's going off the side. So it's insane. But it turns out the quartic is completely solvable by radicals. Great. So are we just going to go through all the numbers up to infinity? Is that even possible? Ooh, foreshadowing. So generalizing this method, Schernhaus was able to do this. Remember, there's that technique of substituting, get rid of the x squared term in the cubic. He showed, in fact, you can make a reasonable change to get rid of the n-1 and n-2 terms of any polynomial, right? So for x3, it's very clearly just reducing it to this. For x4, we get x to the 4. We get this sort of type of polynomial. And Schernhaus was hoping that, having this elimination method together with some of the ideas of Cardano and Ferrari, that he could extend this to all polynomials. But he wasn't having success with it yet. And in fact, E.S. Bring furthermore showed that for fifth degree polynomials, we can also get rid of the x squared term at the same time. So we come to Gauss, the goat. At least according to many people, I think it was growth indeed. But so he comes up, he gives us this theorem, much later on, tells us that it's the fundamental theorem of algebra, right? It says you have any polynomial with complex coefficients, you can factor it completely. You can it definitely can be factored into linear terms. But here's the problem with that proof. Well, first off, it's kind of funny because it's not really all that fundamental. Sort of. Talking about field extensions and you want to fix a closure, okay, but it's not that fundamental. And as far as I know, there's like no algebraic proofs of this fact. They all use like topology, the fundamental group, all this stuff. And on top of that, it's non-constructive. So it doesn't give you a recipe. So never mind things being solvable by radicals. It just straight up doesn't give you a recipe. It says that one always exists. But okay, good luck finding it. I mean, there's ways. So Gauss, his opinion, again, like all these doubters, was that you couldn't solve fifth degree or higher polynomials. But that's kind of curious because he actually found many examples in all degrees that you could. So for example, the nth roots of unity, he expressed these as solvable, as these polynomials as being solvable by radicals. So moving on, creeping along, getting close to the modern day, we've got Lagrange here. And he explored several methods, based on how we figured out the cubics and quartics are solvable. And he was pretty sure that those same techniques would not work for the quintic, but maybe still solvable, right? And so this is actually where the idea of permutation groups first comes from. Now, actually going, speaking about the flourishing of mathematics in the Middle East, they had permutations, basically. Again, when you go back, it's a little anachronistic to say these things. When we talk about permutations today in mathematics, like it would not, you wouldn't read these old ancient works and go, oh yeah, they're obviously talking about permutations necessarily. They didn't have the same notation as we did, but that's effectively what they had done. Anyways, so for example, for these cubic polynomials, he looks at this thing called the resolvent, where he takes the third roots of unity and takes a sort of combination, and he sees if you swap A, B, and C around, what do you get? Well, he found it only takes on two distinct values. So that's interesting. Similarly, for the quartic, he found that it only takes on at most three distinct values. So in both cases, the number of values that it takes on is less than the degree of the original polynomial. But then when he applies this method to the quintic, he finds that now there could be as many as 6 possibly distinct values. So now he's like, okay, I'm pretty suspicious that the quintic can't be solved by radicals. And so, in fact, he was able to show that if every resolvent of a given polynomial always took on more values than the degree, then the polynomial could not be solved by radicals. Of course, the thing is, he couldn't always show that was the case. So the crucial step, is demonstrating that there exists a polynomial of degree 5 with a resolvent equation that definitely takes on more values than the degree. So, but Lagrange, interestingly, there are these other doubters, right? So Gauss found maybe evidence of why the higher polynomials were solvable. Lagrange found evidence that they weren't, and yet and he thought that they still might be. So we all got our beliefs. But after his, he published this paper about the stuff in 1770, and that was just kind of it. He didn't really keep going with it. The first person to actually give us a proof was Paolo Ruffini. So the insolvability of the quintic, so spoiler alert, turns out it's insolvable, is often called the Abel-Ruffini theorem. Now, Ruffini is like technically the first person that has a proof, but his proof had a lot of gaps. He, following the French Revolution, he didn't want to swear allegiance to the French, so they kicked him out of his university. So he's like, all right, I guess I'm just going to be a doctor then. And so he worked as a doctor for a while and basically, worked on this theorem, in the evenings when he came home and was exhausted. And in fact, he kind of kept with this. Eventually, he got an offer at the University of Padua, but he sort of felt this obligation to his patients, so he just sort of kept at it. He made over 6 attempts, trying to clarify his proofs. But even by modern day mathematicians have gone back and looked at all his attempts, and yeah, it's just like a nightmare to read. He sent a proof to Lagrange, apparently, but never heard back from him. And apparently Cauchy received a letter of his, but and allegedly vouched for Ruffini, but I don't know, for whatever reason, it just didn't really catch on. And Cauchy himself wasn't really interested. I mean, dude was a busy man, gave us like everything, but he wasn't really interested in making a cleaned up version for himself for whatever reason. Okay, so the next person who takes a serious attempt at it was Niels Heinrich Abel. So probably mathematicians might be a little bit more familiar with this name. I mean, he was taking care of 8 siblings, but reading the works of Lagrange and Cauchy at the time, and he was one of these super geniuses, like just outdoing his professors the whole time. And in fact, he actually thought at one point that he had been able to solve the quintic, but he showed he eventually found a flaw in it, of course. So now he goes on, he turns around, and after finding the flaw in his proof, he turns around and he does get the correct proof that the quintic can't be solved by radicals. So he sends a copy to Gauss. I forgot to preface this whole thing with how much tragedy are in these stories. Allegedly, this letter was found afterwards, in Gauss's possessions and had never been opened. He also, he tried touring Europe and giving, trying to get people to catch on to his proof, even though it was, arguably better than Ruffini's. But he was actually met with hostility, basically everywhere he went, and even by Cauchy, apparently. So I don't know what was up with the man. But eventually he made it to Berlin, and he made friends with this dude Krell, who had his own journal, and he was like, yeah, clean up this proof and publish it in this journal. And so this journal, there was like big stuff going on. I mean, Jacobi's work on elliptic functions. I mean, this is a whole crazy ordeal that was going on. So people were paying attention, and they finally paid attention to Abel's work. So he got a position offering him a letter offering him a position in Berlin. And it came 2 days after he died of TB. So that is too bad. And his work, started to become known shortly after his death. So tragic. So this other guy comes in the story, Évariste Galois, which, anyone who pays attention to decent math memes, at the very least, you know who this guy is. He read a bunch of Lagrange while he was pretty young as well. But he was a hothead. He failed his entrance exam to the very fancy École Polytechnique, and he still made work towards the solvability of the quintic. Apparently unaware, potentially unaware. I wrote a paper on this once, and it turns out history is hard. But he sort of laid the foundation of what we would nowadays call group theory. So he had this new approach to this, which is developed into modern day Galois theory, which maybe I should make some videos about, because Galois theory is amazing. But he writes to Cauchy. Some people say the letter doesn't exist. Other people was like, yeah, Cauchy wanted him to expand on it, and he didn't, which is kind of a theme in Galois' life. Actually, yeah, right. So Cauchy, there's evidence even to suggest that Cauchy was thinking about presenting to some of his buds about some of Galois' work, but was sick that week. And on this theme of like sending letters to people and then they die, not reading before they die, he apparently had sent one to Fourier, who died before he got Galois' letter. So of course he makes his proof's not catching on, so he makes another attempt in 31, and this is basically that says 1931, but that's not right. That should be 1831. Yeah, Galwa was not alive then. We definitely had way more serious math by 31. Anyway, so basically, in modern terminology, I mean, this is sort of what I was talking about before. Galois group, he's able to demonstrate that a polynomial is solvable if and only if its Galois group is well, now what we call solvable, we call this definition solvable precisely because of this history. But Poisson had, I think he was the main reviewer for his proof. He rejected it, claiming it to be too full of errors. And Galwa, he ended up writing a letter to Chevalier. Yeah, got to work on my French. Which contained a number of his discoveries and some mad ramblings. And he sort of, as you can see here from the quote, I'll just give you a second to read that. He he sort of made this plea to like, hey, get my work out there. In fact, this might have been from one of his last letters before his duel. So I think it's not it's not a secret, not a surprise to many people that Galwa died in a duel. There's some suspicious circumstances surrounding that, but long story short, he lost. He got shot in the stomach, and he didn't even die there. He was found by a passerby still alive, and he died the next day. And that was the end of Galwa. So it does actually turn out that okay, so we can't solve a quintic by radicals, but there's this whole idea of like theta functions, which come up in like number theory in pretty cool ways. Turns out if you toss some theta functions in, then you can solve quintics with radicals and theta functions. But I'm actually having a really hard, like I can go find the original sources, but I'm having a hard time finding good information about this on the internet. And it's interesting, similar phenomena occur in degree 7 and 11, which is cool, but not necessarily the others. There's also these things called Bring radicals. So you can look this up on Wikipedia or whatever. But again, so this is another thing where it's like, yeah, so you can take you have your solvable quintics, and then if you also toss in Bring radicals, which are the roots of these very specific quintics. So if you think back to when I was talking about Chernhouse, it looks kind of similar, not quite the same thing. Then you can solve all these polynomials. Again, it's really hard though to find good accessible exposition on the internet. Anyways, I have a whole bunch of sources because this is just an adapted version of an essay I wrote for a class once. And that's basically it. So if you have any questions, let me know in the comment section below, and I'll see you for some more math soon.